Okay, good morning everyone. Today I'm going to talk about a new topic. So we're going to start discussing deep learning. This will be the main topic for the rest of the course. Okay, so for today's lecture in particular, I'm going to introduce what are deep neural networks. We're going to see that there are two challenges in the early days, and I guess still today, that are important with respect to deep neural networks. So first, the gradient vanishing problem. So how can we optimize a neural network well if the gradient vanishes? And then also, how can we generalize? Because one property of deep neural networks is that they tend to have lots of parameters, and as a result, they're quite flexible. They can fit the data quite well, and then they might overfit. So deep learning has led to some breakthroughs. Today we're going to talk about two of those breakthroughs. So one in speech recognition, and then the other one in image recognition. So since then, there have been more breakthroughs, especially in the context of machine translation and natural language processing in general. Okay, so the first question is, what is deep learning? And perhaps more precisely, what is a deep neural network? So it turns out that a deep neural network is really just a neural network with many hidden layers. So you might ask, so why is there a new name? Why do we call that a deep neural network? Because we've already seen multi-layer neural networks. So this was already proposed back in the 1980s. So at some level, there's nothing new. And so here's the dirty little secret of deep learning, is that the name deep learning really is for marketing. Okay, so what happened is that there was a breakthrough, and then it was using a neural network with multiple layers in the context of acoustic modeling, and then after that in the context of image classification. And then these neural networks, one of them in particular was a convolutional neural net that had been already proposed in the 1980s. So now if you have a breakthrough, people want to know, like, what is it that you've done? Like, what's new? And then if you say, well, I'm using a multi-layer neural network, and it was one that was proposed in the 1980s, then that doesn't add up, right? Like, how can you have a breakthrough with something that is 30 years old? Okay, so now I guess the idea is that if you rename the approach, if you rename what's going on, then people feel like, oh, I've never heard of deep learning. So clearly, the reason why there's a breakthrough is because there is something new. Well, okay, even if it's not just the name, we'll see that there are some new approaches to train those multi-layer neural networks and also to prevent overfitting. But in any case, some of the researchers started calling these techniques deep learning. That caught on, but it was really just a marketing thing. Okay, so what are the advantages of neural networks with multiple layers? Is that they tend to be highly expressive. Now we're going to discuss this again because we've already talked about how if you consider a neural network with a single hidden layer, and then you make that hidden layer arbitrarily large, so potentially infinitely many units, right? Then you can express any function, so you can represent any function arbitrarily closely. So even this question of expressivity is questionable. And at the end of the day, it's really high expressivity in context with, or in combination with, I guess, compactness, or having a way of representing functions succinctly. That's important. Okay, so some of the disadvantage of working with many hidden layers or deep neural networks is how can we train them effectively. So in the past, researchers were quite happy to just stick with neural networks of one hidden layers because they were highly expressive and because we knew how to train them well. And then we'll see that with the gradient vanishing problem, there's some issues where if you have multiple layers, then some of the bottom layers might not be, like the weights might not be adjusted very well or might not change much. and then so training them was really a big bottleneck. Okay, so that's the first problem. The second problem was overfitting. So if you have a neural network with multiple layers, then there will be lots of weights, lots of parameters, and in fact, many of the large neural networks have more parameters than the amount of data. So here, it's no surprise if they can fit the data well. In fact, they might fit it too well, and then this leads to overfitting. So coming up with ways to deal with overfitting was key, and then we'll see today one technique known as dropout for that. Okay, so let's come back to the question of expressiveness. So as I mentioned several lectures ago, if we have a neural network with one hidden layer, and let's say this hidden layer contains sigmoid or hyperbolic units, then we can show that it can approximate any function arbitrarily closely as long as we make that layer large enough. Okay? So we can represent functions quite well, and in fact here there's no apparent gain in having multiple layers, because whatever functions we could represent with multiple layers, we can also represent them with a single layer. Okay? So for a long time, this really kind of biased researchers to simply work with a single hidden layer, while there were actually some advantages in working with multiple hidden layers. The main advantage is that if you increase the number of layers, often the overall size of the network can decrease, and it might even decrease exponentially. So we're going to see one example where there is a function that would require exponentially many units if we have a single hidden layer. But now if we allow ourselves to have multiple hidden layers, then we can represent it succinctly with a linear number of units, so an exponential reduction. Okay, so in fact, let's talk about one of those examples. So I'm going to look at the parity function for this. So the parity function is a simple Boolean or logical function that would essentially return 1 if the number of inputs is odd. So here I've got some inputs. Let's say I've got n inputs in total. I could count how many of those inputs are on, and then if the number is odd, I'm going to return 1. And if the number is even, then I will simply return -1. Okay, so here in this example, I'm going to assume that all my inputs are bits that are either +1 or -1. Okay, this is just out of mathematical convenience. So we're used to having bits that are 0 or 1, but then for the purpose of this example, the bits are +1 and -1. And here I'm going to associate +1 with odd and -1 with even. Okay, so now if I have n inputs, now I can count how many of them are on. If the number is odd, I would like to output +1 and otherwise output -1. And here I constructed a neural network. It's a neural network that has one hidden layer where each hidden unit is essentially a thresholding perceptron that encodes the logical AND function. Okay, so if you recall, when we introduced the perceptron, we saw how it could be used to encode logical gates, like the AND logical function, the OR logical function, the NOT logical function, and so on. So in this case, I'm going to make all of my hidden units to be the AND logical function. And then my output unit is going to be an OR logical function. So here I'm not showing the details of how exactly this is coded, but we've done this before, right? So you can use a thresholding activation function for that. Okay, in this construction, every edge here is going to have some weight as well as here. And now what I'm going to do is set the weights to be as follows. If an edge is black, I'm going to set that to 1. And if an edge is red, I'm going to set that to -1. So unfortunately, the projector is not great. It does not display the colors quite well. But if you look carefully, right, so this is a black edge, for instance. This is a red edge. And the color here indicates what weight I'm going to use. OK, so what I've done is I've set up a neural network where this is fully connected. And the intuition is that each one of those hidden units is going to check whether there's a specific pattern of the inputs that correspond to an odd number of inputs being turned on. Okay, so here we're trying to detect whether the number of inputs turned on is odd. There's various patterns that might lead to an odd number of inputs being turned on. And what those hidden units are going to do is each one of them is going to be responsible for checking one specific pattern where the inputs are odd. And then the output unit is just the OR of the hidden units. So essentially, you see, as long as one of them detects a pattern that is odd, then it means that we've got something that is odd, and this will fire with a +1. If none of them are turned on, meaning none of them have detected something odd, then it means that it must be even, and then this will return -1 for even. OK, and now here, again, all of those hidden units are detecting patterns. So I'm going to write on the board what are the different patterns. And the idea is that for this particular example with 4 inputs, we're going to see that there are 8 patterns of the inputs that are odd. And then each one of them is responsible for one of those patterns. OK, so we've got x1, x2, x3, x4. So one way to look at this is that if it's odd, then I might have 3 units that are on, 3 inputs that are on, and one of them that is off. So this would be one pattern. Now I could change that to be the following pattern, or it could be this pattern, or it could be this pattern. Right? So this gives me all the pattern where I've got 3 inputs that are on. Now, being odd, I could also have just one input that is on. So it could be this pattern, as well as this one, and finally the last one. OK, so I've got 8 possible patterns. And here in my network, so if I take the first hidden unit, you'll notice that it has 3 edges that are black. These have a weight of +1. And then the last edge is red, so it's -1. And then so what would happen is that I would essentially multiply my inputs by +1, +1, +1, and -1. So in this case, you see, it would match, the weights would match exactly this input. So when I take the dot product, it's going to give me 4. If it doesn't match, right, then I'm going to have a dot product that is less than 4. So essentially, my thresholding units are essentially checking for a dot product of 4 versus something lower. If it's 4, then I've got a match. I return 1. If I get something lower, I don't have a match, and I return -1. Okay? So that's essentially how those units are set up. So we're enumerating all the patterns where I've got an odd number of inputs that are on, and each one of them is detecting one of those patterns. Any questions regarding this? OK, good. So in any case, to summarize now, because in the way I've constructed this neural network, I have one hidden unit per pattern that is odd. Now, if I have n inputs, in general, the number of patterns that are going to be odd is going to be 2 to the n minus 1. So now it's clear that I'm going to get a large neural network that has exponentially many hidden units. Okay, so this will not scale very well. Okay, an alternative would be to consider instead a neural network that has many layers. So here I drew my neural network sideways. Okay, so the inputs are here at the bottom, and then the flow of the computation goes towards the right, and my output is right here. Okay, so it's a deep neural network in the sense that it has multiple layers. And the way I'm going to do the computation here is a little different. I'm going to look at subsequences of my inputs. First, I'm going to look at the first two inputs, check if they're odd. So here, I have a similar construction as what I had on the previous slide. Right? So those two hidden units are going to check whether I've got the pattern of 1, minus 1. And this one checks the pattern of minus 1, 1, meaning that there's only one of the two units that is turned on, and therefore it's odd. Okay? So they're checking for odd sequences, and as long as one of them is on, then this OR function will return 1, meaning that it's odd. Otherwise, it returns minus 1, which is even. So this is for the first two units, the first two inputs. Now we can add the third input, and the idea is that now that we already know whether the first two inputs are odd or even, when we combine that with the third one, we can create again two hidden units that will check whether overall the first three inputs are odd or even, and then take the OR again. So that tells me again whether my first three inputs are odd or even. Then I add the fourth input, and I do the same type of computation, and then this will tell me finally whether it's odd or even. So you can see that if I have more inputs, if I have n inputs, right, then I'm simply going to make this neural network deeper, right? So it's going to have more layers. And here it's a deep neural network, but it's a skinny neural network, right? So it only has 2 nodes per layers. And then so overall, you see the size of this neural network is linear in the number of inputs. In fact, the number of hidden nodes is just going to be 2n minus 2. So this scales much better. Any questions regarding this construction? Okay, very good. So yeah, so I guess this is an example where we have a function, the parity function, where if I use a deep neural network, I can do it in linear complexity, so linear space. If I use a shallow network with just one hidden layer, I can still represent the function, but I will need exponentially many units. Okay? And here, I guess I'm not giving you the proof, but there is a proof. You can show that there's no other way of representing the parity function more succinctly. So overall, it will still take you exponentially many hidden units. Okay, so this is an example of one function. Now in practice, there's many other types of functions like this, and the idea is that by having a deeper network, then you might be able to represent some functions more succinctly. Okay, any questions regarding this? Good? Okay, let's continue. All right, so now I've kind of given you at least an example, a theoretical example. In practice, we don't actually care about the parity function. I mean, we wouldn't use a neural network to represent the parity function. So there's simpler ways of dealing with parity in practice. But still, this is an example. And now what about actual things that we would do with a neural network? So for instance, if we're doing computer vision, where let's say we've got some faces and we want to recognize a person based on its facial features within a crowd. Okay, so we might have a training set that corresponds to a bunch of images, and then we would feed in an array of pixel intensities, and then every layer is going to compute some intermediate values, and then at the output, we would produce a classification that might tell us whether this is the person we're looking for or not. Okay, so if we work with such a neural network, one thing that might happen So in fact, what has been observed with deep neural networks is that they tend to compute features that are simple at the bottom and then become higher level as we go through the network. So here, just to illustrate, you see when our inputs are essentially vectors of pixel intensities, the first layer might compute some features that simply corresponds to little strokes or little edges in different directions, or otherwise little corners. So some very simple abstract features. Then those features will get composed to compute some higher level features. And again, just to illustrate, in the context of faces, you might observe some features that corresponds to parts of a face, like a mouth, like an eye, like a nose, and so on. And then the next layer will produce features that are even higher level. So for instance, we might have different types of faces. So some smiley faces, some sad faces, faces with a mustache, faces with glasses, and so on. So different types of faces. And then finally, the output would just produce what we're interested in. If we're interested in recognizing a person or doing classification of some kind, then that's what would be produced here. But the point is that those hidden layers are often capturing features at different degrees of granularity. They're not always interpretable, but what has been observed is that they tend to be low-level features at the beginning and then higher-level features as we go. So here the benefit of depth is that if you've got a problem where it's not clear what the features are, now your neural network can learn by itself what the features should be or what might be a good set of features for your task. And here, just to be clear, so in computer vision, up until deep learning, what was the state of the art was that anybody, a practitioner for a given task, would always first start by deciding what features should be used, and these features would be crafted manually. So people would come up with different types of functions that would correspond to features, a bit like when we talked about generalized linear models, where you have to come up with some phi function that gives you features. So here again, people would design those features by hand based on their expertise, their domain knowledge, and so on. And then based on those features after that, they would apply a classifier or some regression technique depending on what their goal is. And so this was the state of the art, but then the real bottleneck was designing those features. This was a manual task. It was something that really required a lot of intuition and was not obvious at all. Now, with deep learning, what happens is that those features are effectively learned as part of the network. So this was really unthinkable at the time, because really the mentality, and people had been trained to do this, is that you would come up with features manually and then do the machine learning on top of that. And here what deep learning allowed us to do is to say, well, forget about handcrafting all of those features. Let's just work with the raw pixels, and then the different layers of the network will effectively learn features. Right? So here we've already talked about how if you have just one hidden layer, you can think of it as computing some nonlinear basis functions that are adaptive, right? And then the second layer can compute a linear combination of these things. So here it's the same idea, but now we've got this at multiple levels. So we've got basis functions or features that are being learned at every level. And these things are adaptive, so we don't have to specify them too carefully. I mean, there's still a question of what the architecture of the network should be, because this will influence what the features are going to be like, but there's more flexibility in that sense. Okay, any questions regarding this slide? Okay, good, let's continue. Okay, so in terms of breakthroughs with deep learning, so Jeff Hinton was the pioneer at the University of Toronto, And back in 2006, he designed the first effective algorithm to train a deep neural network. And at the time, what he did is that he was working with what are known as restricted Boltzmann machines. And then he would stack different layers of restricted Boltzmann machine to make a deep neural network. And then he came up with a way to train them layer by layer. Okay, so this way he could train a lot of those stacked restricted Boltzmann machines together. And this was the first time that someone was able to train effectively a deep neural network. In 2009, he applied this to acoustic modeling, and he effectively replaced mixtures of Gaussians by those stacked restricted Boltzmann machines, and that led to a breakthrough. So there were some benchmarks where people had been testing speech recognition techniques for years, if not decades, and then on those benchmarks, there was like almost no improvement for a decade. And then so when he tried these techniques, there was an important improvement, and then companies including Google, Microsoft, and IBM immediately started using those stacked restricted Boltzmann machines, and then that led to further improvements. Now I didn't stop there, so around 2013, then recurrent neural networks became popular, and especially what are known as long short-term memory networks, or LSTM networks, that we're going to talk about later on. And using those, so at this point, restricted Boltzmann machines were replaced by recurrent neural networks. Then Google showed that its error rate reduced from 23% down to 8%. And Microsoft, in 2016, achieved an error rate of 5.9%, which was unthinkable because on some benchmarks, this was the same as human performance. So this was really revolutionary because speech recognition was a difficult task. People had been working on this for decades. It was working, but not very well. It was always clear that humans were better at recognizing speech than a machine. And nobody was thinking that we could get a machine to match human performance anytime soon. And then so using these techniques, then this was achieved in 2016. Now obviously this is with respect to a specific benchmark, but then today you can experience speech recognition through your smartphones and many other devices, and it works. It's still not perfect, but it works a lot better than it used to, and this is thanks to all the improvements in deep learning. Okay, so speech was the first breakthrough. The second breakthrough came in image classification. So back in 2010, there was an important challenge known as the ImageNet Large-Scale Visual Recognition Challenge. So this was a challenge where you give the computer a bunch of images, and you want the computer to simply classify those images among 1,000 categories that correspond to different objects. So for instance, is there a car in this image? Is there a cat in this image? Is there a plane in this image? And so on. So there were 1,000 categories that generally correspond to different objects, animals, and so on. And can you get the computer to recognize or classify these images accordingly? And when you think about this is something very basic, right? So as a human being, if I give you an image, you look at it, you know immediately what's in there, and you can recognize what you see, right? Now the computer, I mean, it was kind of very frustrating because all this work in computer vision, still we could not get computers to take as input an array of pixel intensities and tell us what is in that image. So this was the challenge that was proposed for many years and was really difficult. And here, I guess, yeah, the difficulty comes from the fact that if you are given a sequence of pixel intensities. Like even as a human being, if I give you numbers that correspond to those pixel intensities, you could not look at those numbers and figure out what is in the image, right? If I give you the image, then you can see it, but I guess the computer is actually working with the pixel intensities, and the question was really, can we come up with a way to get the computer to do this type of recognition? Because that's a basic task. If you can't recognize what's in an image, you can't do much with images. Okay, so in 2010, the error rate for these 1,000 classes was 28.2%. So this was the winner of the competition in 2010. In 2011, the error rate went down to 25.8. And then in 2012, something special happened. So the error rate went down significantly. It went down from 25 to 16%. And so here, this was the winner. Now the second best entry was still around 25%. So at the time, a lot of people questioned the results. They thought there must be an error. How can somebody beat everyone else by 9%? I mean, this was, a major improvement. And then when they looked at the solutions, it turned out that, you see, up until 2011, the state of the art was to do feature extraction. So somebody would manually come up with a bunch of features, and then they would train a classifier on top of that. At the time, support vector machines were really the state of the art. They were considered some of the best techniques for classification. So the winning entry in those 2 years was essentially a combination of features with support vector machine. But then in 2012, Jeff Hinton's group submitted an entry called AlexNet. So it was essentially a convolutional neural network, and then it reduced the error to 16%. So this was really quite outstanding. And in fact, this convolutional neural net was very similar to another neural net called LeNet from the 1980s. So we're going to see that, I guess, maybe the innovation was not so much in the architecture or in the network itself, but in how to train it and how to prevent overfitting. In any case, at that point, researchers understood that, okay, there's something there in those neural networks, and then perhaps we can improve them further. So then some more sophisticated architectures were designed, error rate kept on going down, and then the human performance for these types of images was around 5.1%, and already in 2015, the best entry was better than human performance. So again, nobody would have expected that a few years ago, simply because the error rate was so high. We were nowhere near human performance, and then in a span of few years, we ended up beating human performance. And here I guess humans are not perfect because some of those classes are not easy to distinguish. So there are classes that correspond to different races of dogs. And if you're not a dog person, like I can't tell for most dogs what race they belong to. So I would make mistakes, okay? So there's a lot of classes like that unless you've got the right domain knowledge, you would have difficulty. And that's how humans are not capable of achieving 100% accuracy. Okay, so this is what happened. And now something interesting to note was that the improvements that were achieved, if you look at how deep were those networks that ended up winning the competition every year, there was a trend where the depth of the network was increasing as well. So in 2012, it was a network of 5 layers. Then in 2013, 8 layers, then 19, 22, 152. Today, we have networks that have more than thousands of layers. Okay, so here, there's lots of ingredients that go into improving the results, but there was a clear trend, and that helped to justify again the need for deeper networks. Okay, any questions regarding this slide? Okay, very good. Let's continue. Okay, so now let's talk about what are the innovations that needed to take place so that convolutional neural networks and more generally speaking, deep neural networks could be applied and could lead to those breakthroughs. Okay, the first problem is in how we train those neural networks. So we saw that we can use backpropagation. So backpropagation is essentially a form of gradient descent, and you can apply this to any type of neural network. If it has multiple layers, there's no problem. You can still just do backpropagation, do gradient descent. The problem is that when you do this, though, you're going to suffer from what are known as vanishing gradients. So what we mean by vanishing gradients is that if we have a network with inputs here that produce some outputs here, then when you compute the gradient or the partial derivatives of all the weights associated with those edges, so for the last layer, the partial derivatives are of some reasonable magnitude. Okay? So it's going to be a fairly large magnitude because if you change those weights, they influence the output, so therefore the partial derivative is fairly large. But now if you go back one layer, those partial derivatives tend to be smaller. Okay, so the gradient would be here of a medium magnitude. And if you go back one more layer, then it tends to be even smaller. So the further back you go, the gradient tends to be smaller and smaller and smaller. So what this means is that if you have a really deep neural network, right, the bottom layer does not get trained. If the gradient or if the partial derivatives of those weights is negligible, it's so close to zero that when you take steps in that direction and then you take steps that are proportional to the magnitude of those partial derivatives and it's negligible, then you're not changing the weights. If you're not changing the weights, it means that whatever you start, when you initialize the weights here, it remains the same. It never really changes, and then it becomes questionable whether you really need those layers, because those layers, the weights would typically be initialized randomly, and then doesn't matter how we initialize them, they don't get changed, so they're computing something random, so how can that be something good? Right? So this was an important problem that really prevented researchers to effectively train those neural networks that have multiple layers. So something needed to be done to get the weights even of the bottom layers to be adjusted, because at some level they're like the initial computation. They provide the simplest type of features, and if that doesn't get optimized, then it becomes questionable whether the whole approach is going to work. Okay, so part of the reason why the gradient was vanishing was due to the type of activation function that was common at the time. So in the early days of neural networks, the most popular type of activation function was the sigmoid activation function. So we've talked about it a lot throughout the course, right? So it's a function that starts around 0, rises, and approaches 1 asymptotically. Now another type of activation function that was also popular is the hyperbolic tangent activation function. This one starts at -1, rises, and approaches +1, also asymptotically. And if you look at those two functions, their shape is similar, right? So they have this sort of S shape, right? And the main difference is just that this one goes from -1 to +1, this one goes from 0 to 1. But now there's something problematic about these functions that we're going to see in a moment with respect to the gradient computation. So here, two important properties of those functions is that first, their output is always of magnitude less than 1. So the sigmoid function, it produces a number between 0 and 1, so clearly it's less than 1. The hyperbolic function produces a number between -1 and +1. If you take the absolute value of that, again, it's less than 1. Now, it's not just the output, but also if you look at the partial derivative or the gradient of those functions. So if we look at the gradient of the sigmoid, So anywhere along, the gradient would correspond to the slope, okay? And here the slope is always less than 1 again. Okay, so the slope in this region is close to 0, then it becomes higher. It doesn't actually surpasses 1, so it remains less than 1, and then again it approaches 0 here. Same thing for the hyperbolic function. That function too has a slope that is always less than 1. Okay, so now if we come up with a simple toy neural network that is very skinny, so it's a network that just has one unit per hidden layer, okay? And let's just make it a general neural network that has a weight with respect to each edge, and then has an activation function that, let's say, corresponds to the sigmoid activation unit. Okay, so it's a toy neural network, and now this one is skinny, but it's a deep neural network because it has multiple layers. Okay, so now if we compute the gradient will consist of a partial derivative with respect to every single weight along this chain. And I've written down here what is the computation that goes into finding the partial derivative for each weight. Okay? And if you look carefully, these partial derivatives are essentially products of factors. Each factor is either the partial derivative of the sigmoid, the output of the sigmoid, or a weight. But now we just saw that the sigmoid has an output that is less than 1, a partial derivative that is less than 1, and then what is also common is to initialize the weights to be between -1 and +1. So in magnitude, the weights, at the beginning at least, are also less than 1. So now if you multiply a bunch of factors that are all less than 1, you get a number that becomes smaller and smaller and smaller as you multiply those factors. And if you look at the partial derivatives, right, so as we go back into the neural network, so the bottom layer has a long product of numbers that are all going to be less than 1. And then, and so on. So I guess here you see, if we consider the length of those products, right, because we multiply more and more numbers that are less than 1, those partial derivatives get smaller and smaller. They're not necessarily going to be smaller than each other, but overall they tend to get smaller and smaller, and that's how we observe this gradient vanishing problem. So here it really means that, I guess, the first weight has less of an effect on the output y, and at some level it might not be surprising because, I mean, there's so many other things that happen in between that its impact is not as important, so that's why the partial derivative is small and can be really close to 0. Okay, so this is an example, but generally speaking, this is what we tend to observe, not just with skinny network, but networks that have a certain width. When we make them deep, then as we go back into the layers, right, then those weights tend to have less and less of an impact, and then the first layer is the one typically that has the smallest partial derivatives. Okay, any questions regarding this? Okay, very good. So let's continue. Okay, so now that we understand how the gradient vanishing problem arises, the next question is what can we do to resolve it? So today we have many solutions. Some of the popular ones include pre-training, using a different type of activation function, such as rectified linear units or max-out units. Another solution is to use skip connection, and then you can also use batch normalization. So today I'm going to talk about one of those solutions, so rectified linear units and max-out units, but just for your understanding, so at a high level, when we talk about skip connections, that essentially means that you have your neural network, and instead of connecting nodes from one layer to the next, you might connect a node to another node that is several layers higher up, essentially creating skip connections, so you're skipping over some of the layers and creating paths that are shorter, right? So the depth of the neural network effectively is determined by those shortest connections, shortest path. And then so if you've got a short path, then the gradient vanishing problem is not as important because the gradient will propagate through those short paths. So this has become quite popular in terms of architectures. And then another possibility is to do normalization. So at every step, if we want to make sure that our gradient is not too bad, when we look at those functions, you see the gradient would actually be close to 1 if we were in this region. And then if we're in this region, the gradient is close to 0. So if we renormalize all of our values to be in a range where the gradient tends to be close to 1, then that helps as well. So here batch normalization is this idea that you're going to renormalize the data from a batch to have mean 0 and variance 1. So it tends to produce data that will be effectively in this range. Okay, so in any case, I'll talk more about rectified linear units and max out units. Here the idea is that, you see, we identified those activation functions as problematic for creating gradients and partial derivatives that tend to be fairly low. So what if we consider different types of activation function? Perhaps we won't have this problem. Okay, so one idea is to consider activation functions of the following form. So we're going to consider an activation function h that is the max of 0 versus the linear combination a of the inputs. Right, so if you recall, the notation that we've been using throughout this course is that for a unit, we first take a linear combination of the inputs. We call that linear combination a, and then we pass this through an activation function h. So here, when we pass this through the activation function h, we're just going to take the max of 0 and a. So effectively, you see it's going to return a again unless a is negative, then it just returns 0. Okay, so this function is illustrated as the blue curve in this graph. So it's a function that has an elbow shape like this. Okay, so it's 0 when a is negative, and then after that it rises linearly because a is a linear combination of the inputs. Okay, so this function has some good properties because when we look at its output, when we look at its partial derivative, it is not going to be a number between 0 and 1 all the time. So in fact, the output can be anything. I mean, it can be anything even greater than 1. So then that will help. And then if we look at a partial derivative, so the gradient of that function is either going to be 0 when we're in this range, and then 1 we're in this range. Okay, so here I'm looking at a partial derivative with respect to a. And the partial derivative, you see, in the flat range, the slope is 0. And then in the linear range, the slope is 1. So here, I guess it's not obvious, right? You might say, well, I still have a possibility of a gradient at 0. Doesn't that make the gradient vanishing problem worse? Because now the gradient is just going to vanish to 0 in one shot, and then anything that happens before that doesn't matter, right? But the point is that in a neural network, we typically have lots of connections, lots of units, and then sure, maybe there's some range where your gradient is 0, but then the rest of the range, the gradient is 1. So in the linear portion here, the gradient is 1. And now the idea is that when you have lots of connections, some of those connections are going to have a gradient that vanishes to 0, but other connections are going to have gradients that are 1 for every edge. Okay? And then when you have these entire paths with a gradient that is 1, then it's not vanishing. And here the point is that it's okay to have some paths that vanish as long as some paths do not vanish. And we achieve that with this here where we have a gradient of 1. Okay, any questions regarding this? Okay, you guys are very quiet today. Hopefully this all makes sense. Or maybe you guys are already experts in deep learning, and so you know all of this already maybe. Okay, so, all right, so these are the rectified linear units, but when you look at them, these rectified linear units are not smooth. There's a discontinuity here at 0. And a lot of people did not feel comfortable with these types of units at the beginning. Because you see, if we're going to use gradient descent to train a neural network, we want to be able to compute the gradient everywhere. And unfortunately, we won't have any gradient at 0. Today, it turns out this is not a big deal because we can use subgradients. So there's a way to obtain a value even if we are at a point where there's a discontinuity by considering subgradients. And then it turns out that in practice, it happens almost never that you're precisely at such a point because numerical values are such that it's not going to be exactly 0. So you will typically be somewhere along this linear range or the flat range here, and then you'll have a gradient. Nevertheless, if we want to get a soft version of this, then there's a function called soft plus. So this function is in green here. It approximates the rectified linear unit by using the formula log of 1 plus e to the a. And here, if we replace e by a different base and we make that base arbitrarily high, then it will essentially get this function to become arbitrarily close to the rectified linear function. Okay, so in that sense, it's a soft version of the rectified linear function, and it happens to be smooth, continuous. You can compute the derivative everywhere. And then at the beginning, a lot of people thought, wow, let's use that. That feels better because I'll have a gradient everywhere. Now the problem with this function is that by making it smooth like this, now we have a gradient that is less than 1 everywhere. So here, if you look at the slope, right, so the slope that's 1 is what corresponds to the blue curve, but then the green curve only approaches the blue curve, and it approaches it with a smaller slope. So therefore, the gradient is less than 1. So it has a gradient that is less than 1 everywhere, and it doesn't help. Okay, so here, making rectified linear units smooth does not help to get rid of the gradient vanishing problem. And it turns out anyway, at the discontinuity, we can use subgradients to compute what we need. And so in practice, rectified linear units have become really the popular approach, whereas soft plus has remained just something interesting from a theoretical perspective, but it doesn't help with respect to the gradient vanishing problems. Okay, so yeah, that's a great question. So whenever we use a rectified linear unit, you see the portion that ends up being 0. It's the same as saying that whatever we computed before can be ignored. Right? So it means that part of our network is actually computing something useless because it's just going to become 0 anyway, and maybe we should have just deleted that. Right? And now if there's a large portion of this, aren't we wasting a lot of space, and why do we work with such networks? So, okay, for a given set of inputs, yes, we're going to have a large portion perhaps of the network that could have been ignored, but that's for a specific input. Now you take a different input, and now for a different input, when you get to a unit, then that unit now might be in the linear part. So the idea is that across the space of all possible inputs, chances are there exists some inputs for every unit that will make it produce something in the linear part. So overall, the entire network is still useful. Yeah, so okay, so here you see we take a linear combination of the inputs, so even if the weights are fixed, right? So if I feed different images for classification, that means I've got different inputs, And then as a result, for some of those inputs, I'm going to be in the linear range. For other inputs, I might be in the 0 range. But then you see for any unit, typically there will exist one input, maybe one image that happens to be in the linear range. Okay, any other questions? Yeah?
Is there any other advantage of Pelu? Like one is this vanishing gradient problem. So is there any other advantage of using this?
Yeah, the question is, are there any other advantages for rectified linear units? So there probably are. So, I mean, they have become one of the most popular type of activation functions today. I mean, it was really because of the gradient vanishing problem. And then even when the gradient doesn't vanish, then often you can train them faster. So you often need fewer steps of gradient descent to train them. So I guess at least in practice, this is really the main advantage. There's probably other advantages, but yeah, they don't come to my mind right now. Yeah?
In this case, our gradient must have just two values, 0 or 1. Right?
Mm-hmm. Yeah, just 0 or 1 for the gradient.
Yeah, and I was just thinking that it's very good like just adding amount of eta to the previous value or not. Because when we're updating, we have W is equal to W minus eta or step.
Yeah, so eta is our learning rate. So yeah, it will affect the size of the step that we take.
Yeah,
So.
Since the gradient always is 0 or 1, we're adding or not adding.
Oh, okay. So here, I guess I need to be careful. So when I say the gradient is 0 or 1, this is with respect to A, where A is the linear combination of the inputs. Now, in practice, what we want to do is compute the gradient with respect to the weights, not with respect to A. Okay? And then so effectively in practice, the gradient is not exactly 1 or 0 because you would use the chain rule to compute the gradient with respect to A and then the gradient of A with respect to the weights, right? So then it would not be exactly 0, 1 because of that. So it would be a different value. But in any case, this conveys the main message. Yeah. Okay, let's continue. Now, rectified linear units always give you a shape where you have a 0 part whenever the linear combination is negative, and then a linear part whenever the linear combination is positive. But now you might feel like maybe I want to have a generalization of this. What if I want to have just several linear parts, and maybe I don't want to have the 0 part because that feels somewhat arbitrary, somewhat constraining, right? So what about having multiple linear parts and letting them be anything we wish? So this leads to the max out units. So max out units are a generalization of rectified linear units. And here the way I depict them, well, okay, so the formula is the following. So you take the max of different linear combination. So here we have some inputs, and then we consider a first linear combination with weights denoted by 1. Then a second linear combination where we have a second set of weights denoted by 2, and then a third one here. And in practice, we can have as many linear combinations that we want, and then we just take the max of those linear combinations. So here, max out units are more like an aggregate unit. So if we want to represent them in the most basic way, we would have some identity units. So essentially no activation unit, or so no activation function in each one of those units. And then you take the max on top of that. So here, a max out unit would essentially correspond to the aggregation of a hidden layer of identity units with a max unit. Okay. So yeah, we don't have to work with this aggregation, but it's still an interesting way of thinking about it. And then the shape of such a construction would look like this. So here, let's say that I've got 3 linear combinations. So each linear combination corresponds to a line. And now when I take the max, right, it's essentially, it corresponds to taking the upper surface, okay, of those 3 lines. So that's what the shape is for a max out unit. And you can see that this is a generalization of the rectified linear unit, because the rectified linear unit always has a 0 part followed by a linear part. And here with the max out units, if I set all of the weights for one of my linear combination to 0, then I would get a 0 part, and then I can have another part that is linear. So in that sense, I can always encode a rectified linear unit by a max out unit. Okay, any questions regarding this? Good? Okay. All right, so let's talk now about the second problem that needs to be resolved to do deep learning effectively, and that is the problem of overfitting. So here we have high expressivity, and that comes from the fact that by having multiple layers, then we have lots of parameters. In fact, in some applications, some of the networks are so large that there are more parameters than there are data points in our training set. So here, it's no surprise if neural networks can fit very well the data, but then they're at risk of overfitting. So some of the solutions include regularization. We talked about this several times in the course, where what you do is you just add a penalty term that says, let's minimize the magnitude of the weights, and this will keep the weights small, it will keep them constrained, and this is one way of doing, to prevent overfitting. Now I'm going to talk about another technique known as dropout, and then yet another technique could simply be to say, to do data augmentation, to add more data. So one way of preventing overfitting is that if you train with more data, right, then you're less likely to overfit. And here data augmentation refers to this idea that you can often take a data set, perturb it to construct more data points that are different, and then it helps to generalize. Okay, so dropout is a new idea that was proposed by Jeff Hinton's group and ended up being critical when they won the ImageNet challenge. So here, the idea is that we're going to randomly drop some units from the network when we train. So when we train, we have a neural network, and then instead of just computing at every node some values, now some of those nodes we're going to drop them, which means we're going to remove them from the network, and effectively that's the same as saying that we replace their values by 0. And then so doing those changes is going to force the network to be robust in a sense, because it's the same as if you have a network and you mutilate it by removing some nodes, and now forcing the network to still perform well despite the fact that you remove some nodes at random. So if the network manages to do that, then it must be robust to changes, and then it will have a much harder time to overfit. Okay, so how do we do these mutilations? One idea is that at training time, what we do is for each iteration of gradient descent, we're going to drop some of the input units with some probability p1. Here, this would often be a small probability like 0.2. And then for every hidden unit, we might also drop it with some probability p2. And there, the hidden units are not as critical as the inputs. So here, often a higher probability like 0.5 might make sense. So you train your neural network with this mutilated version, right? So once you've removed these nodes from the network, then you compute your gradient, and then you train the weights of whatever is left in your network based on that. And then you repeat for every data point. So like this, you mutilate the network at random and train. And then overall, the network will still evolve, but it will have to be robust since at any point in time, some of the nodes might be removed. So this is what we do at training. Now at test time, when we do a prediction, what we do is now we're going to use the entire network. So we won't remove anything. We won't drop any units. So we're going to use everything. But now there's a problem because when we remove some of the input units, this was effectively the same as making some of the inputs 0. And then the overall magnitude of the linear combinations that would feed into the next layer would be reduced because some of those inputs were zeroed out. So now, when we use the entire network, now because nothing is being zeroed out, then those linear combinations tend to be higher. So we're going to have to correct for this because otherwise the network, you see the following layers are not used to seeing such high values. So then the trick is that you say, well, since I'm not removing anything, I'm simply going to multiply every input unit by 1 minus p1. So this is effectively rescaling them. You see here we drop them with probability p1. So now if we don't drop anything, on average it would be the same as reducing the magnitude by probability 1 minus p1. And then we do the same thing for the hidden units. Okay, so let me draw an example on the board for this. Okay, so let's say that I've got 3 inputs, 4 hidden units, and then 1 output. And let's say that this is a fully connected network, and now I'm going to train with dropout. So what I'm going to do is for my first data point, I'm going to take a random number generator and then decide at random which inputs I'm going to zero out. In other words, I'm going to drop from the network. So here, if I use probability 0.2 for dropping input units, what I'm going to do is essentially sample my random number generator. If I get a value that's less than 0.2, then it means I remove that unit. If it's greater than 0.2, I keep it. So here, let's say that we sample, we get a value greater than 0.2, so we keep this one. Let's say for the next one, we sample, we get a value less than 0.2, so now we drop it, which means that we remove it from the network. And then the last one, let's say we sample, and again we keep it. So then we would be left with this for our inputs. Then we do the same thing for the hidden layer. Now typically the dropout probability is higher, like 0.5. So perhaps the first one, here we sample our random number generator. In this case, we can think of it as a coin, right? So with probability half, perhaps we drop this one. So I would remove it. The next one, let's say that when I sample, I end up keeping it. Maybe the next one I keep it too. And maybe the last one, I remove it. Okay, so then my network would be mutilated in this way. And now I would also remove all of the edges that are dangling, that are not connected to anything. So whatever is left now is going to be the network that I'm going to use to do a step in the direction of the gradient. So whatever is left of the network, I'm going to do back propagation on it and essentially take one step in the direction of the gradient and update the corresponding weights. So this is for one data point. For the next data point, I'm going to redo this where this time, so if I just put back those nodes, when I sample, perhaps this time the first node is going to be dropped, the second one kept, the third one kept. Maybe here I keep this one, drop this one, keep this one, drop this one. So I would end up with a different network. I would again compute the gradient with respect to this different network, update the weights, and keep on going. Any questions regarding this? Yeah?
In my propagation, do we update all the weights or just the remaining weights?
So here we would update only the remaining weights, because the weights that are on edges that are dangling, I would remove them. So here, I'm not showing you which edges I'm removing because my drawing, I mean, all the edges are crossing each other, but effectively, I would remove all the edges that are dangling. Therefore, those weights would not get updated. Yeah?
What would happen if you remove all your inputs?
So what would happen if we remove?
All the input units?
Yeah, well, okay, good question. Yeah, what happens if we remove all the input units? So then we've got a big problem, right? So here, this would effectively mean that the input would be 0. Now, the odds of this happening is typically very low because, okay, in practice, you would typically work with lots of inputs. If you think of images or if you think of text, often the inputs are going to be very long. So you're going to have on the order of thousands, if not millions of inputs. And now the odd that every single one of them gets removed is negligible, right? And I guess this is true as well for the hidden layer. What if everything gets removed? Then there would be, it would be effectively 0 from that point on. Now in practice, this is very unlikely to happen. Yeah.
What are we doing during the test time?
Okay, so at test time, now what we do is we consider all of our units, right? So we work with the full graph. And now what we do is instead of dropping any units, we multiply their magnitude by 1 minus P1 for this layer, and here by 1 minus P2 for this layer. The intuition is that you see, normally I've got 3 units, right? P1 of them, on average, are going to be dropped. So what's left really is 1 minus P1 of them. But now if I keep everything, then I should perhaps reduce their magnitude by 1 minus P1 so that on average I have linear combinations that are on the same scale as when I was doing the dropping. So that's the idea for multiplying by 1 minus P1 and here 1 minus P2. Yeah?
If you're dropping input units, does that not mean you're just training on less data, like less features of the data?
That's right. So if I'm dropping some of the inputs, then it means some of those features are being zeroed out, and that can impact our accuracy, right? So in fact, we're forcing the network to become robust with respect to features where some of those features might essentially be dropped. Yeah?
But wouldn't that be a bad thing because you're training on less data?
Yeah, well, okay, so it's a good and it's a bad thing. So it's a good thing because then we're not going to overfit easily. And then it's a bad thing because if you happen to have some inputs where every single feature is unique and there's no redundancy in your features, if you drop one of them, then it might make the problem impossible. You might not be able to obtain good accuracy as a result of that. But now if you think of some applications like if you're working in computer vision, images, the pixels, there's a lot of redundancy because neighboring pixels tend to have similar values. You drop one, it's fine. You still have the neighboring pixels, right? And then in text, often we embed our words into some vector space where the embedding will have like hundreds of values, and those values, often there will be some redundancy again. Okay, so on this slide, I've got here the algorithm laid out. So this summarizes what we just did on the board. So essentially, you have an outer loop for every epoch. Inside every epoch, you go through each training example where you take a step in the direction of the gradient. But when you compute this gradient, it will be with respect to a mutilated network where we apply dropout. Okay? This mutilated network, we obtain it by sampling some Bernoulli variables. So these Bernoulli variables are going to be a value 0 or 1. If I sample a 0, then what I'll do is I'll multiply the 0 by some corresponding value in my network, and this will have the effect of zeroing out or dropping that unit. Okay? So here I'm going to use this symbol to indicate element-wise multiplication. So I sample some binary variables according to a Bernoulli distribution like this for every layer. And what I do is then, if I take like our first layer, you see my inputs, I multiply them all by 0 or 1. When I multiply by 0, it effectively drops out the unit. Okay? And I do this at every layer, so I'll multiply what is being computed at that layer by a vector of zeros and ones, and this is now my new function. I compute the error and the partial derivative with respect to that mutilated network, and then that's how we do the training. And then the main difference for prediction is that you see now I don't multiply by the vectors of zeros and ones. Instead, I simply multiply by a constant, 1 minus p1, or 1 minus p2 or 1 minus pl, so depending on which layer, which effectively adjusts the magnitude of our values so that those linear combinations are on the same scale. Okay, so the intuition behind dropout is that, again, we're making the network robust. Now, from a machine learning perspective, we can actually think of dropout as a form of approximate ensemble learning and also approximate Bayesian learning. So here, the idea is that with respect to each iteration, when I compute a mutilated network, you see, if I end up with a mutilated network where some of the nodes are dropped out like this, right, we could think of this as essentially one hypothesis, one possible function that could encode what I'm trying to learn. Now, the next iteration, I get a different mutilated network, so this is a different hypothesis. And then at the end, when I combine them, so at the end, when I look at my entire network, I can think of it essentially being the average of all those mutilated networks. And it's the average because you see when I multiply by 1 minus p2 or 1 minus p1, I'm readjusting essentially what is being computed, and that can be thought as like some way of merging what is being computed on average by all those networks. So if I took one mutilated network, computed its output, did the same thing with the next one, computed its output, and so on, and then just took the average of these things, then it would be equivalent to multiplying by 1 minus p1 or 1 minus p2 and so on. So this is roughly speaking, right? So this would be an approximation in that sense. So here in ensemble learning, we're going to talk about this later in the course, is this idea that you can come up with lots of hypotheses. They each make some predictions, and then you take an average of those predictions to get a better outcome. So we can think of dropout as doing this, and this is also similar to Bayesian learning. So in fact, here some researchers demonstrated rigorously that dropout is approximating some computation with respect to a deep Gaussian process. So we talked about Gaussian processes. There is actually a notion of deep Gaussian process that corresponds to deep neural networks. And now if you do Bayesian learning, the computation would be intractable. And then when we do dropout, we are effectively doing some approximate computation in a Bayesian way. So that explains, or at least that justifies also theoretically, why this can work well in practice. Okay, let's stop here, and next class I'll continue with the remaining slides. All right, so last lecture I introduced deep neural networks. So we saw some of the basics, and in particular some of the challenges that had to be overcome so that we could effectively train neural networks with multiple layers. Now, this has led to some breakthroughs, and in particular, when we look at some applications, the first application where there was a major breakthrough was speech recognition. So we're going to talk a little bit more about this in a moment. The second one is image recognition or image classification. We're going to talk about that one too. And then it went on after this. So in machine translation, there was a revolution as well based on recurrent neural networks. Now in control and also in reinforcement learning, deep learning has become quite important. So today we could say that wherever there's a lot of data or there's a complex problem, then deep learning has become key. Okay, so if we look at speech recognition, the state of the art up until 2009 was actually to use a hidden Markov model with a mixture of Gaussians. So here, the problem of speech recognition is that we have an audio signal, and then we're trying to recognize out of this either a sequence of phonemes or otherwise a sequence of words. So a hidden Markov model, we're going to talk about this next lecture, is a model where there's some hidden states, where each hidden state essentially can correspond to a class, for instance, a phoneme, or otherwise a word. So it's an important probabilistic model that allows us to recognize sequences, like sequences of phonemes and words. And beyond the hidden states, there's also some observations that correspond, for instance, at the audio signal. And in the framework of probabilistic modeling, historically, these audio signals were captured by a mixture of Gaussians. So there would be some features that are extracted, and then there would be a distribution over those features in the form of a mixture of Gaussians. And part of the reason was that Gaussians are nice. Gaussians can also be expressive if we have lots of them. So in a mixture of Gaussians, we can, in fact, capture fairly complex distributions. So this was the state of the art. Now, back in 2009, Jeff Hinton, with his research group, essentially revisited this idea and thought, okay, what if we replace the mixture of Gaussian by a deep neural network? In fact, what if we insert here a stacked restricted Boltzmann machine? So we've got our observations that correspond to the audio signal, and then we have here different layers that correspond to restricted Boltzmann machines, and they provide an alternative to mixtures of Gaussians. Now, we're not talking about restricted Boltzmann machine in this course, in part because they are not anymore the state of the art, but at least back in 2009, this was what led to a breakthrough. So essentially, normally in sequence modeling, you have a hidden Markov model or some sort of sequence model for the things that we want to recognize. And then there's another probabilistic model that typically captures the observations. So now we're replacing the mixture of Gaussians by stacked restricted Boltzmann machines. So this was some sort of hybrid model between a probabilistic model, so a hidden Markov model, and then a deep neural network. When this was proposed, this led to an important reduction in the error rate. So in this table, what we can see is that the classic approach, which was a Gaussian mixture model with a hidden Markov model, achieved an error rate. So this is a percentage of words that were erroneously recognized. Okay, so here, obviously, we want this to be as low as possible. And then so we've got different tasks. And then for each of those tasks, you can see the error rate was still fairly high. But then by replacing the Gaussian mixture model by a deep neural network, then here there's a reduction of roughly 9%, here a reduction of roughly 7%, and so on. So there were reductions across the board for most tasks, most benchmarks. And these reductions were actually quite significant. So hidden Markov models and mixtures of Gaussians had been around for many years, in fact, decades. And the error rate was not really reducing much. So every year maybe there was a small gain of a fraction of a percent. So really like this was stable and there was not much improvement. So here, reduction of 9, 7%, and so on. And this is across the board. This was like really, really significant. So then, based on this, several companies, including Google, Microsoft, and others, started leveraging deep neural networks. And this really led to the renaissance of neural networks. Any questions regarding this slide? Okay, good. All right, the second breakthrough came in 2012 with image recognition. So in particular, can we classify images in terms of different categories representing different objects? So here, this breakthrough was based on a special architecture that we're going to talk about in the next set of slides. And this was a type of network known as convolutional neural networks. So, okay, I've got an example here of a convolutional neural network. Basically, it takes as input an image. So the image is essentially a 2D array of pixel intensities. And then we've got different layers. These layers correspond to convolutions. At the end, we have some dense layers where everything is fully connected. And then finally, we have an output layer that computes the class that each image might belong to. And in the context of the ImageNet challenge, there were more than 1,000 classes. So here, the output layer was quite big, so 1,000 outputs. And then the idea is that all these intermediate layers that are computing convolution, we're going to see in a moment, that they correspond to computing features or detecting features at different level of granularity. Okay, so convolutional neural networks really changed the way people were thinking in the context of computer vision. And in order to really achieve this breakthrough, because convolutional neural networks at some level are not completely new. They had been around since the 1980s, but then really what made them work well was the addition of rectified linear units that we talked about, and also dropouts. So these were two important components. And then another aspect was the use of data augmentation that can help in terms of making the recognition invariant with respect to, let's say, location or rotation and so on. Okay, so in 2012, there was this challenge that had been ongoing for a couple of years. And then the best entry was submitted by this team led by Jeff Hinton. And they achieved an accuracy, or in fact here an error rate, of only 16.4% with an ensemble of 5 convolutional neural networks. And now if you increase that ensemble to 7 convolutional neural networks, then it went down to 15.3%. Now, this was a significant reduction compared to the second best entry. The second best entry that year had an error rate of 26.2%. So this is a gap of 10%. And it means all the other entries, because there were many participants in that competition, all the other entries were even worse than that. So again, this was a significant reduction. The competition had been ongoing for a few years, and really like 26% was more or less what people were expecting. These were essentially the best results that had been obtained the previous year and were being obtained otherwise that year again. But then they reduced the error rate by 10%. So this was a significant drop. Now here, 16% error is still high, but if you take into account the fact that there were 1,000 classes, then getting the right class is actually quite difficult, even for human when there's 1,000 classes. And here, when we say top 5, what we mean is that it would be considered a correct classification as long as the algorithm returns the correct class among its top 5 classes. So it's a bit like if you're asked a question, you're allowed to provide 5 answers, and as long as one of your answers is correct, we're going to say that you've got it right. Okay? So here, this is how things are measured. So you're looking at the top 5 classes, and then 16% of the time, the correct class was not among the top 5. So you can see how challenging this was. Okay, so to illustrate, there are examples of images here. For instance, this is an image where the correct class is a mite, and then the algorithm with the convolutional neural network returns 5 classes: mite, black widow, cockroach, tick, starfish. And then what we see on the left side, those bars, that corresponds to some confidence score, the probability that each class is the correct one. So you can see that in general it tends to work well. So like container ship was recognized with high confidence. Here, motor scooter, and so on. So, so in general, it does quite well. Now it's not perfect, and then obviously you can find some examples where it did misclassify, but overall these are the type of images and some of the classes that it could choose from.